All right, so for homework 3, part C for separations, we are going to start off by deriving two different equations, the Fenske equation and the Underwood equation. And then after that, I'm going to go back into coding and determine the minimum reflux ratio for a certain feed. We are going to do this with 4 components this time rather than just 2. So now we're finally talking about a non-binary system. We're going to define our liquid fraction feed and recoveries. So I'm going to get into those derivations now. The Fenske equation helps us determine the minimum number of stages. So that's, if you want to think about it, that's kind of what we are solving for. Since we're using 4 components this time, I need to introduce a concept called the light key and heavy key. Abbreviated LK and HK. Basically, the heavy key is the least volatile component that you want to be present in the bottoms product, and the light key is the most volatile component that you want in the distillate product. So our vapor composition of the light key, this R means I'm talking about the reboiler, and that is equal to our K partition coefficient time of the light key times the liquid composition of the light key. So our first equation, we have the vapor composition of the light key in the reboiler. I'm going to actually label that as RE because I don't want to confuse that with reflux for any reason. So that is equal to the partition coefficient of the light key times the liquid composition of the light key in the bottoms. That's our first equation right there. And we can write a similar equation, but for the heavy key. So we have our partition coefficient of the heavy key times the liquid composition of the heavy key in the bottoms. And what we want to do is divide those 2 equations. So we get the vapor composition of the light key divided by the vapor composition of the heavy key. I'm going to put RE up here just so we know that for both of those that is in the reboiler. And that is equal to the exact thing I just wrote. We're just writing it a little bit differently because we divided it. And I'm similarly putting an exponent. It's not really an exponent. I'm just labeling that that is for the bottoms for those values within the parentheses. And actually, those don't need to be included, but we know that the ratio of these partition coefficients is equal to alpha, which is our relative volatility. So I'll actually rewrite this using alpha. And I'm actually going to put a subscript here as well, that this is the light key over the heavy key, because we want to specify what we're talking about when we say relative volatility when we have 4 different components. As we know, the vapor leaving the reboiler has the same composition as the liquid leaving the stage above it. So at infinite reflux, which basically means the reflux is infinite and the distillate is 0. We would have our liquid composition of the light key divided by our liquid composition of the heavy key to the n. That is the stages. Here I'm going to label that as n min, but from now on I'm just going to put it as n, equal to our relative volatility times x light key over x heavy key, and that is the bottoms. And actually I am just going to keep that as n. It's technically not n min, but we're just talking about stage n right there. So if we have the vapor composition of the light key over the vapor composition of the heavy key to the n, and I'm also just going to write alpha from here on, and just know that that is the ratio of the light key to the heavy key times x, the liquid composition of the light key over the heavy key, and to the n. And if we want to do n minus 1, which would be the next stage, we would have that to the n minus 1. This alpha gets squared. And then this is also, sorry, that is not, so that is to the, not to a power, but that is for the bottoms. And actually, I think that this should also be the, so we have the light key over the heavy key, those liquid compositions, D being the distillate, alpha to the n stage, times x divided by, or xlk divided by xhk, the heavy key, that is in the bottoms. Then what we want to do is take the logarithm of our xlk over xhk and the distillate over xlk over xhk in the bottoms, and take the log of our alpha to the n, so that we can solve for n. So I'm actually going to rate this in a way that makes more sense, but that would be n times the log of alpha. So we have n min is equal to the log of our ratio of the liquid composition of the light key to the heavy key and the distillate over that same ratio of the light key and heavy key, but in the bottoms. And that's all divided by the log of alpha, our relative volatility. And I'm going to make this red. This is our Fenske equation. So now that we've done the Fenske equation, we want to do the Underwood equation. I apologize if I skip some steps like throughout this as I'm deriving, but the end result should be the correct, I guess, like equation. So this Underwood equation, similar to what I said about the Fenske helping us to determine n min, this helps to determine the minimum reflux ratio required. So if you saw part B of this homework, towards the start of my graphing you would have seen a pinch. As you can see in this diagram from Wikipedia, this point where the Q line is and the rectifying and stripping lines connect is far enough away from the equilibrium curve that you don't get a pinch. But what I was trying to show was if they are too close, you get a pinch in that area. So sorry, that is a horrific drawing, but it kind of gets my point across, I hope. And so if you're at a pinch, you would see that xn plus 1 is equal to xn, and yn plus 1 is equal to yn, so you're not making any progress whatsoever, and you're kind of stuck. So they're basically equal to each other there. From the rectifying section, we know that Vyn plus 1 is equal to Lxn plus dxb. Sorry, that should be dxd, not dxb. But yeah, so we have that there. We would say Vyi is equal to L times yi over ki, because remember that k is y over x. So x is equal to y over k. So we're just replacing that there. And then we're doing dxd. So technically, since we have so many components, I do need to include an I after my x, just to denote which one I'm talking about. So I'll try my best to keep that in when I'm continuing to write, but if I forget it, that's why some of these equations have that. So we can isolate y, the vapor composition of component I, is equal to d, the distillate times the liquid composition of component I in the distillate, divided by v, the vapor flow rate, minus L over K, the liquid flow rate, over Ki, and Ki is Yi over Xi. And we can also simplify that to Ki times the distillate times the liquid composition of component I in the distillate over the vapor times that Ki minus L. Next, we want to divide by Kr, which is just a reference. Typically, people will use the heavy key as a reference, but we're going to call that Kr. So we simply divide everything by Kr. We can simplify that a little bit to be V times Yi is equal to the relative volatility of component I, which is that right there, times the distillate times the liquid composition in the distillate, divided by our relative volatility that we talked about, minus L divided by V times Kr. So we're going to say that this phi is equal to L over V times Kr. To further simplify this, and we can say that the vapor is equal to the distillate times the summation of our relative volatility times the distillate composition over the relative volatility minus that phi that we have there. This was from our rectifying section, and now we are taking something from the stripping section. We have the bars again, because remember those bars signify that we are in the stripping section rather than the rectifying section. So we have L bar times xn is equal to V bar times yn plus 1 plus the bottom's flow rate times the bottom's composition of component I. And then similarly to what we did for the rectifying section, we have our L bar times yi over ki is equal to V bar yn plus 1 plus the same thing as above, basically. And then we solve for yi. So that is our yi there, and we have V bar times yi is equal to bxb multiplied by ki over kr, which remember is our reference partition coefficient there. You have L bar on in the denominator divided by V bar times that reference k, and then we are subtracting that again, and we also know that negative V bar is equal to the summation of that relative volatility here times the bottoms times the liquid composition of component I in the bottoms divided by our relative volatility once again. And we are going to make so we had our phi here. We're going to do a psi, and this psi is equal to the liquid divided by the V times the Kr, which is right here. And this is just from like rearranging things, but we have that relative volatility minus psi. If we say that phi and psi are equal to each other, then that's where we get our Underwood equation from. We have 1 minus q times the feed is equal to the relative volatility times the feed flow rate times the composition of component I in the feed divided by our relative volatility minus phi or psi. We're saying that those are equal, so it doesn't quite matter. And then we notice that we can cancel out the f's, and we are left with 1 minus q. Remember that q tells us the amount of liquid in the feed. And we end up with our Underwood equation. So the Q is our feed quality. We know L plus D divided by D is equal to R plus 1 divided by R being the reflux ratio. And so that is also equal to this, which we have up here. But basically, this is going to help us to figure out what R min we need. Now we are in the final section for this part of the homework, but basically we want to determine the minimum reflux ratio, so we're using that Underwood equation for an equimolar 4-component feed, so a quarter of the feed is each of the components. And with these relative volatilities given, a 50 mole % liquid feed fraction and those are our recoveries that we need to take into account. As always, I have my import from class. The very first thing we're going to want to do is set our alpha values that were given, which was 2.5, 2, 1, 2.5, 2, 1, and 0.7. We also want to set our feed flow rate. Again, I'm just using 1, but in reality, it wouldn't be 1. 1 mole per time is not quite a lot. But anyways, I'm going to set that to 1 for the ease of things. And now we want to make sure that our code knows that this is an equimolar feed ratio, so our Z. And we're just putting 0.25 4 times. And we also want to define that our mixture of the feed itself is 50 mole% liquid feed, so 0.5. We also want to set the recoveries. So for our recovery of the light key distillate, we wanted 0.95, so 95%. And our recovery of the heavy key bottoms is 96%. Now what we want to do is we want to calculate the component flow rates in the distillate. So I'm going to put that below here. It would be the feed times this right here, and I'll explain after I type this out. And I actually forgot to do this, but the light key, and I'm putting IDX, the light key is component 2, because remember in a list, this is 0, and this is 1. So it would be the component with the relative with the relative volatility relative to the heavy key of 2. And obviously this is going to be our heavy key. It has a relative volatility of 1 because it's compared to the heavy key. And if this is the heavy key, the ratio of it to itself is 1. So that makes sense. So the heavy key ID should be 2. And I realized I forgot that because it is absolutely needed for this part right here. So this right here is the components lighter than the light key. This is our light key, heavy key, and heavier than the heavy key. And we're doing 0 here because we are assuming that none of it goes into the distillate. And now we want to normalize our WD by dividing it by the sum of everything in that array. Now we want to define an Underwood function given a phi, which we talked about earlier. And that's also what we're trying to solve for, because we need phi to determine the minimum reflux ratio, which is what we are trying to solve. We want to return, we're doing JAX for the automatic differentiation that it can do, because we don't want to do that ourselves. Alpha, our relative volatility, times the times Z, which was our fractions, divided by alpha minus phi minus 1 minus q. And then after that, we want to vectorize our Underwood calculation. And now we are ready to make a figure. This figure is going to help us to determine what phi value is the correct phi value to use. And we're going to make some test points for phi that I'm going to call phi's. And we are arranging that just below our minimum alpha and just above our maximum alpha, so that we don't miss any points there. We would like to add a scatter where the x is the phi's, y is the Underwood vectorized version. We want to update the y-axis so that we don't have like a crazy, I guess, range, because we're just trying to look at the roots, so where the lines cross the x-axis. And we need fig.show. So let's see what that looks like for now, if it works, which it looks like it does not. Y-axes, and so there we go. And before I actually run our Underwood like function to find the phi, I'm going to explain it graphically first. So right here, we have the vertical lines are our alpha values. So we have one at 0.7, 1, 2, and 2.5, so that looks right. And these phi's over here, we're going to ignore because we are paying attention to the light key, which is 2, and the heavy key, which is 1. So we're looking at this line here. And we want to know where this line crosses the x-axis. So we know that once I type out our phi root equation, if it's not about 1.39, then we have a problem. So I'm going to go ahead, shift enter there, and now we can solve for that phi root. And notice that the x is at 1.5, which is in between the light key and the heavy key. And then if I do phi underscore root, that should and I need to delete that extra scalar at the end. It should just be dot root. And so there we go, we have 1.39. So that tells us that is the correct phi root to use. Now the question is, how do we find the minimum reflux? Because that's what we were doing, that's our goal, I guess I should say. So that's our last step. I'm going to call this R min. It's equal to the sum of our alpha times the distillate composition divided by alpha minus our phi root, which we calculated above, minus 1. Now we just want to output our R min. And after putting this through, we can see that our R min is at about 1.66. So basically what that means is if we use any reflux ratio less than about that, we're going to see that pinch, and then we are not going to be able to, I guess, the reflux ratio isn't high enough, so our purity will suffer, and everything will suffer. Our column will not behave as we want it to get the purity or recovery, etc. that we want. But obviously you can go above that ratio, just not below. And that's actually it for part C. So we started by deriving both the Fenske and Underwood equations. The Fenske was kind of more for finding our minimum stages, and the Underwood equation for the minimum reflux, but mostly like how to solve for phi to get the minimum reflux. And so we displayed that in code to find the minimum reflux for that equimolar 4-component feed. So thank you for watching. There's one more part to this homework assignment in which we will dive into Ponchon-Savarit method, which is similar to the McCabe-Thiele that we did in the previous video, but we use this Ponchon-Savarit when we cannot assume that constant molar overflow, just basically more non-ideal situations. So thanks for watching, and I'll see you in the next video.